Hello everyone. My name is Jagrut and I am going to explain about capacitors. Capacitor is a passive element which stores energy in the form of electric field whenever a current is passed through it. From this we understand that capacitor is a charge storing element. And the ability to store electric charge in a capacitor is called as capacitance. Capacitance is denoted by the letter capital C. And we can see here that the typical representation of a capacitor can be represented in these two ways. So a capacitor, from this we can say that capacitor is a element which stores electric charge, and we can use electric charge wherever we want. I mean, in whatever conditions when we need electric charge, which to provide electricity. So now, for example, let's consider a capacitor with a positive terminal and a negative terminal. And let's apply a voltage V. So the current passing through the capacitor is given by C into dV by dt. And here C is the capacitance, V is the voltage, and T is the time. Time. So let's see. From here we can say that I, if we see this formula, I equals to C into dV by dt. Now we can clearly say that I is a function of time. So the current I varies with the time, and so from this we can say that if, for example, if time is current is not varying with time, then it will become an open circuit. So the only condition when which where current will not depend on time is if the voltage is DC voltage. If it is an AC voltage, then it will definitely vary with time, and the voltage will also keep on changing. So we can get a current in an AC circuit. So now let's understand the construction of a capacitor. So capacitor is nothing but two conducting plates separated by a distance d. And whenever we apply voltage, there will be charge accumulation on each of the sides. For example, in here, one side is charged with positive charge, and the other side is charged with negative charge. And the capacitance of this capacitor is given by C is equals to epsilon naught A by D, where epsilon is the permittivity of the electric field. So we know that electric field passes from positive charge to negative charge. So the permittivity of the electric field is known as the ability to permit the flow of electric field is called as permittivity. And from this we can, from the formula C is equals to epsilon naught A by D. The area is A is the uh, 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 the area A is the area of the conducting plates in this figure. So for example, let's consider this area A is slightly slightly increased. For example, now the area which we have to take is only the area between the total. The area which is covered by both the plates. For example, if it is increased slightly in this way, where the cursor is moving. So now, for example, this area won't be considered whenever we solve any kind of problems or any numericals or any applications in anywhere. Okay, so we won't consider this area, we only consider the area which is covered by the both the plates. So now let's come into the charge stored in a capacitor. So the charge stored in a capacitor is directly proportional to the applied voltage across a capacitor. So for example, let's take that Q is directly proportional to V. Now if we remove the proportionality symbol, we get a constant which is C, and C is the capacitance, like we had discussed in the previous slide. We discussed about the capacitance is nothing but the ability to store the charge. So from the above definition, we can write this formula Q is equals to CV. Now the energy stored in a capacitor is given by half. qv half c into v square. So if we rearrange the c into v from this above formula q equals to cv, then we can also write this as half into 1 by 2 into q into v. So now let's discuss about the different combinations of capacitors. First one is the parallel combination of capacitors. So we need to understand what actually parallel means. So in parallel combination, the only condition which has to be satisfied is that both the voltage across two capacitors is same, just like resistors. In resistors also, the parallel combination means is that the voltage between voltage of two resistors should be same. So in this way, now we can say that the voltage across C1 and C2 is equals to V. So now let's imagine a current Q, the a charge q is passing through from this point A, and now it will be divided into q1 and q2. Now q2 is passing, q2 charge is passing through capacitor C2, q1 charge is passing through the capacitor C1, and again according to the law of conservation of charge, or even KCL, now q1 plus q2 will again be equals to q. So now let's take this condition q is equals to q1 plus q2. So q1 is equals to c1 into v1, where c1 is from the above formula q equals to cv. C1 is the capacitance of the first capacitor, and v1 is the voltage applied here in the first capacitor. So now we know that V1 and V2 are both equal. Why? Because the arrangement is parallel combination. So V1 and V2 are equal. So let's say V1 and V2 is equals to V. Now Q by V is equals to C1 plus C2. If V1 and V is taken to the LHS denominator. So Q by V, if we do this, Q by V is equals to C equivalent of the whole capacity. I mean, this whole setup. So C equivalent is equals to C1 plus C2. So now if there are, for example, let's say, assume that there are more than two capacitors. Again, we have to do the same procedure, but in this case, if there are more than two capacitors, then we'll get the total sum of the number of capacitors. For example, if there are n number of capacitors with different capacitance, then C equivalent will be the sum of all the capacitances. So this is what we get in this is the effective capacitance in when we connect capacitors in parallel condition. Now let's come to the series combination. So uh, to- uh, uh, if two capacitors are said to be in series, if the charge passing to the C1 capacitor is equals to the charge passing through the C2 capacitor. So now let's assume a charge q is passing through the point A. Now the same charge will be passed to C1, and again the same charge will be passed through C2 also. And again, if we look at this point B, again same charge Q will be present at this point also. So now let's take the applied voltage. For example, let's assume that we have applied a voltage V. Now a capacitance V1 will be applied at capacitance. A voltage V1 will be applied at capacitor C1, and V2 will be applied at capacitor C2. So V is equals to V1 plus V2. Now let's take V is equals to Q by C1. From the above formula, Q is equals to CV. If we rearrange it, we will get V is equals to Q by C. Similarly, V2 is equals to Q by C2. And here Q is same because the charge passing through both C1 and C2 is same. So now if we bring the Q to the denominator in the LHS side, we get V by Q is equals to 1 by C1 plus 1 by C2. So 1 by C1, we know that Q by V is the equivalent capacitance C between the 2 points. Now instead of V by Q, we can write 1 by C, and this C is the effective capacitance between it is the effective capacitance of the series combination. So we got 1 by C is equals to 1 by C1 plus 1 by C2. So if, for example, let's take there are, I mean, n number of capacitors in series. So the effective capacitance will be equal to the sum of reciprocal of individual capacitances. That will be equals to 1 by C equivalent. And is the if we do the reciprocal of 1 by C equivalent, we will get the C value. And when we solve this entire equation, then we will get C effective equals to, we'll get the total sum of this. So in this way we can calculate the effective capacitance in a series combination. Thank you.